Okay, the chapter 3 practice problems document that you sent me.
Yeah.
Okay. Let me create new note. This one open. Um, share screen. Okay. You had a question about the second one right here.
No, the first one.
The first one right
Yeah.
here. Given the relative reactivities of various kinds of hydrogens, the major product expected from monobromination of 2-methylbutane would be what? So this is a free radical halogenation reaction. Are you familiar with the reaction and mechanism?
Sorry, you cut off.
Are you familiar with the free radical halogenation reaction and mechanism?
A little bit.
Yeah, so free radical halogenation is going to substitute a hydrogen from an from a hydrocarbon with a halogen. So the reagent that you are going to have is X2, light or heat, and your product is going to be a haloalkane and strong acid HX. Right. You're substituting a hydrogen with a halogen. Like we're substituting this hydrogen with this
Mhm.
X, which comes from X2. This hydrogen here is going to bond with the other X to make HX, right? Because we have two X in the reagent, X2, 1, 2 in the product. This hydrogen here makes a bond with one of the X's. The other X makes a bond with the R right here. It takes the hydrogen's place like that. Right. The mechanism has 3 parts to it: initiation, propagation, and termination. But this question here isn't asking for the mechanism, it's asking for what the major product would be. Right. So I'm going to give you some examples. Let's say we just have this right here, and I'm going to draw out one of the hydrogens of that middle carbon right there. And let's say I react this with Br2 and light. The product is going to halogenate the alkane, meaning that we're going to add a halogen to this alkane right here. And then we're going to have HBr as a side product. Right. So the reason why I put it at this carbon instead of the other carbons is because of this relative reactivity chart. Right. This is the relative reactivity chart for bromine. But a quicker way to remember this is that the type of carbon you have, primary, secondary, or tertiary, is going to be preferred by depending on what halogen you use. If you use fluorine, it's going to prefer to go to the primary carbon usually. If you use chlorine, it prefers to go to the secondary carbon. If you use bromine, it prefers to go to the tertiary carbon. Right. So let me give you an example of this. If I have something like this and I react this with Br2 and light, the bromine could either go to any of these carbons right here, right? Because any of those carbons has at least one hydrogen that it could replace. But if we look at the relative reactivity, bromine usually wants to go for the tertiary carbon, right? So at this molecule right here, we have this tertiary carbon right there. So our product is gonna brominate that carbon. We're gonna add a bromine on that carbon right there, which substitutes this hydrogen right here, right? And our side product HBr, like that. But there is like a way to figure out which way is preferred through using this relative reactivity chart, right? So I'm going to copy and paste this whole chart and explain to you how you could figure out what's the major product, right? So let's say that you have this problem right here. I'm going to draw out the molecule in bond line form like this. Oh, which is the same thing as I drew out here earlier. That's this thing right here. And then he put R2 on the reactant side, but like this thing is basically saying, like this thing is the same thing,
Oh, okay.
right? Like instead of the BR2 being on the arrow, it could be on the reactant side like that, right? So based on what I showed you earlier, the major product should be this, where the bromine is on the tertiary carbon, which the answer is if you want to figure it out, because there is a more mathematical way to figure it out, right? So here's the more mathematical way to do that. First, products you could form from this reactant here, right? So we see that we could form these unique products right here. Show what I mean. These are 4 different products that we could have. Am I cutting off still? Can you hear me fine?
Yeah, you're cutting off.
Oh, I'm cutting off. Okay, let me connect. Hello, hello. Can you guys hear me?
Yeah.
Am I still cutting off?
No.
Okay, let me know when I'm cutting off, and I'll switch to a different Wi-Fi.
Okay.
So the things that I drew out here are the different unique products that we can have from this reaction, right? And I'm going to draw out the reaction in bond line form like this, right? Where these are 4 different unique products that we could have. Because if we look at this carbon right here, it has 3 hydrogens, but we only worried about 1 hydrogen, right? And if this 1 hydrogen here is being substituted by bromine, we get this product right here, right? Because if we look at this carbon right here, this carbon had 3 hydrogens. If we substitute one of the hydrogens with bromine, we get this, right? Because now it has 2 hydrogens and 1 bromine, right? Where this one bromine here substituted this hydrogen right here, right? Does that make sense?
Yeah.
Right. We can also put a bromine here instead, right? Where this carbon used to have 2 hydrogens, but now it has 1 hydrogen, where one of the hydrogens got substituted by the bromine like that. That's the other unique product that we could have. The other one is going to be on this carbon, where we have 1 hydrogen, but we substituted that 1 hydrogen with that bromine right there. The other one is going to be on this carbon right here, where we substitute this hydrogen with that bromine right there, right? But you might think of like why we didn't draw this one right here. Like why didn't we draw this product, right? This is because this and this is the exact same thing. It's not unique. They're the exact same thing because of symmetry, right? So you know how this is a single bond right here, the one that I'm highlighting in the laser is a single
Yeah.
bond. That single bond can do free rotation. So when I rotate it, think of wait, it's better if I draw it like right here to show. Like if I rotate that single bond right there, keep this side the same, right? That side, I'm gonna keep stationary. It's gonna stay still. If I rotate it, these two groups are gonna swap into each other's place like that. Right? Like think of it like rotating the groups like this. They're going in circles. If I'm rotating this bond, these two groups here are gonna move into each other's spot. Does that make sense?
Yeah.
Right. So this is the same thing as this, but it's just this bond here is just rotated, right? This thing went to here, that thing went to here. Like that. Right. Now this is here, that's there. It's the same thing, but just rotated. Right. So that's not unique. That's why I didn't draw out that one. Okay, so now let's look at each one individually. How many hydrogens did this carbon have right here? The one that I'm highlighting in red, in the original molecule.
3.
Yeah, 3. So 3 hydrogens could have made this product, right? 1, 2, 3. Those 3 hydrogens there could have made this product right here. Now, what type of carbon is this? Primary, secondary, or tertiary carbon?
Primary.
Yeah, primary. So then you look at the type of carbon, which is primary, and then look at the relative reactivity, which is 1, right? So you use that to multiply it with the amount of hydrogens you could have used to make this product, right? So 3 times 1 is 3. That's the relative abundance that can make this product right here. Let's do the same for this one right here. How many hydrogens could have made this product right here?
2.
Yes, that's right. What number do we have to multiply this by to get the relative abundance?
80.
Yes, because we have a secondary carbon. We look at the reactivity chart, and then we multiply it by 80. 2 times 80 is 160, right? So right now, we see that there's a higher chance of forming this product more than this product, right? The number here is representing how many like of this will we form compared to the other one, right? So this will make more sense after we finish the whole thing. What would you do for this one here?
You would multiply 1 hydrogen with 1,700.
Yes, 1,700 because we have a tertiary carbon right here, right? Which is 1,700. What about the first one? The first one is going to be a little bit trickier.
3 hydrogen multiplied by 1.
Yeah, so that's the tricky part. 6 hydrogens are actually going to be able to make this one right here.
How is it 6?
3 from this carbon, 3 from this carbon. Because you know how earlier I said that this carbon is the same as this carbon because this bond can do free rotation? Like they can swap into each other's spots, right? Like if I were to substitute the bromine with this hydrogen right here, I would get this product right here. But that product is the same thing as this one right here, just rotated, right? We just rotated that bond to get that thing. This is the same thing as this, but just rotated.
So when it's the same, you just count it together?
Yeah, count it together, right?
Okay.
So it's going to be 6 hydrogens times 1 because this is primary. So that would be 6. Right. So just look at the number here. And whichever has the highest number is the one that's most likely to be formed. The one with the lowest number is the one that's the lowest likely to be formed, the least likely to be formed. Right. So this is the least likely to be formed. This is the most likely to be formed because it has the highest number. Right. So the answer should be E. Is it E?
Yeah, it's E.
Yeah. So that was the mathematical way to do that whole thing. But this chart here generalizes it, and it usually follows this trend, right? The bromine prefers the tertiary carbon.
If we use that chart, instead of doing the math way, like both answers would be the same?
Yes.
So we didn't have to do all that math.
Yeah, you didn't have to do the math, but he like gave you this chart, so he might ask a question of like do the math of how you figured that out, like show your work, because he gave you this table, but you didn't have to use this table to figure it out.
Okay, so like for question 9, it's kind of similar. Would the answer be A because there's 3 carbons around it, and then the other ones are just like the primary,
Yeah,
and
it
that
should
would
be
be
A.
like an easier way
Yeah,
instead of doing all the math.
yeah.
Okay.
Is that the answer?
A is the answer, yeah.
Okay, yeah, yeah.
And then for 10 too, it would be A, right? For the same reason.
Yeah, because this time we're using fluorine, and based on the chart, which I showed you earlier, fluorine prefers to be on the primary carbon,
Yeah, primary.
right?
Okay.
Primary carbon. So that's the general thing, right? General chart that you could use without doing the
Okay.
whole math. So this one
That
should be
makes sense.
A.
Okay.
Yeah. Okay. Nice. Hey, Elysia, do you have any problems, questions?
Hi. Well, I was just wondering if we can go over like just some of the series midterm one. I kind of uploaded it into the
Uh-huh.
files. I don't really have specific ones, but I think maybe the ones that we can focus on are ones that you would think are challenging. I
Yeah.
think I'm pretty comfortable with like naming structures.
Mm-hmm.
Um, Maybe like resonance may be a hard one, but I'm not sure if Nasiri normally gives like challenging ones of that.
Mm-hmm.
Um,
Yeah. Wei, she used to be the head TA for Nisiri for like so many years, and she
right.
was the one that wrote her exam. So like these exams are gonna be very similar to like what Wei uses probably.
Okay.
Right.
Yeah, that's what she said. So she
Uh-huh.
said her questions are going to be very similar to Nasiri's, and some of them are also going to be based on the textbook as well.
Mm-hmm. Right, right. See these images. Oh, you sent the one with the key.
Yeah. Do you want me
Huh.
to upload one with without the key? Cause
Mm,
there wasn't one without it, so I kind
mm-hmm.
of had to block it out myself.
Oh yeah, no, it's okay. It's okay. We could do this with the key, and then I'll copy and paste the ones that don't have the key, so then we could try it without looking at the key first. Uh-huh.
Okay. Do you have the one without the key?
Uh, no, I don't have it.
Okay, I'll upload it right now as you pull
Uh-huh.
up one.
Yeah, thank you.
Mm,
Yeah, yeah. And then I'll import it and then we could work through that instead. But I'm
okay.
still sending it through this document so we could reference it
Okay.
later.
Thank you.
Hmm. How are you feeling about your midterm tomorrow?
Uh, it's on Friday, but
Oh yeah, on Friday. Oops.
yeah.
Yeah.
I think I understand the material for the most part. I think all I need is like practice just to make sure I'm not making any like small mistakes.
Hmm.
Um, I was kind of going over like today I was like working on acids and bases and I was like kind of working on a worksheet that was a bit confusing. Um, like I can understand it for the most part, but like kind of trying to understand the movement of resonance
Mm.
structures
Yeah.
from like basic and acids.
Hmm.
Um, it was a bit hard. I was trying to ask like a few tutors, but it,
From A to C, like the drop-in ones.
yeah, but they weren't able to give a full
Oh
like
shoot.
explanation. Yeah.
Yeah. Are there specialists still there, like Mariah, Edna?
Sadly, no.
Oh no.
Yeah.
Yeah,
I mean,
dang.
maybe it's because of the times that I went.
Mm-hmm.
Maybe it's because I think Mariah
Does
said
her online ones?
yeah. I think she does online.
Yeah. Okay. Yeah. Let me know when you are finished uploading the blank copy.
I just finished. Let me know if you it went through.
Okay. This one's exams. I see. I see it. Okay. Send the copy. Add import. Import. Next one. Okay, let's start off with the questions that you had first that you tried to get. So, let me share my screen. Start. Okay. Okay. So the questions you have were they on this practice midterm?
Oh wait, can you still hear me?
Yeah, I can hear you. I can hear you.
Okay, sorry. Can you repeat your question?
Yeah. Were the questions you had at the ATC from this practice midterm?
No, if you want, I can upload it.
Hmm.
But I mean, you can
Yeah.
still pick a problem that you find like hard, and then we can go over it together.
Yeah.
Um, it's because I guess I'm a bit worried about like the series exams because I heard they're a bit more challenging. I think
Yeah.
understanding acids and bases are I would say more general to me because I feel like I could figure out on my own. It's just like
Yeah.
explaining it is a little bit difficult,
Yeah.
but
Uh-huh.
yeah.
Uh, did you go over chair conformers, chair flips yet?
Um, could you point it out?
Yeah. Like axial equatorial. Did you go over that in lecture?
Would that be part of chapter 3 or chapter 4?
Oh shoot. I don't know off the top of my head.
Okay.
Yeah.
I know that we finished with like selectivity and radical halogenations with
Uh-huh.
fluorine and bromine. Um, we also covered chlorination of higher alkanes. Um, other radical halogenations of methane. I
Hmm.
don't think I don't think so.
Yeah. So if you haven't gone over that, then I don't think it should be on the exam this
Mm-hmm.
Friday. This is nomenclature. This is chair conformer. Bond line structure for C2H4. Lone pairs of electrons, dual structure, reaction. Okay, yeah, let's do the predicted product reaction.
She
So this is, huh?
oh sorry.
Yeah.
She did make an announcement saying like the practice midterm one, she hasn't covered like Q or like question 2C, question 2D, 4C, 4D, and 7D.
Yeah, yeah. That's the confirmer stuff. Yeah, yeah. So that's good. Okay, so that won't be on the exam,
Mm-hmm.
then. Yeah. Okay. Okay. So the first reaction here is free radical halogenation, where we have this alkane and we have F2. What type of carbon or what substrate does fluorine prefer to attack, to substitute with?
1 degree,
Yeah, 1 degree, one primary carbon.
right?
This is a tertiary carbon, so we won't add the fluorine there. The fluorine will be in either one of these three carbons here that I'm circling. Right.
Right.
So the answer is going to be something like this. Right. And then you might even put HF if you want. Right. Which
Okay.
is a side product of this reaction. Okay.
So it doesn't matter, like I guess which fluorine in this case, or like which carbon in this case it attaches itself to.
Yes, it
Okay.
doesn't matter which primary carbon it attaches to. They're
Right.
all the same. They're all going to be the same,
Okay.
right? Because if you were to draw this product, it would be the same thing as this product right here. Oh my God. And then that would be the same thing as this product right here,
Right. Okay.
right? Because this bond right here has free rotation. So when we rotate that, those three groups right here
Hmm.
can rotate into each other's spots.
Right. That makes sense.
Now, the next one, we have a Cl minus, because whenever you see Na, it is always associated with a positive charge. So whatever is
Right.
attached to it is negatively charged,
Hmm.
right? And we have Hi right here. This Cl minus here is going to be our base. This Hi is our strong acid, right? So in the
Okay.
acid-base reaction, this Cl here is going to deprotonate the acid and give us HCl and then an I minus, or we could say NaI, like that. And that's an acid-base reaction.
Okay. So you said the chlorine is gonna want to deprotonate the HI acid.
Yes. Uh-huh. Right. The chlorine minus is the base that is going to deprotonate the Hi acid.
Right. And so it goes to the hydrogen.
So it uh grabs the hydrogen. The Cl
It
here,
grabs the hydrogen. Yeah.
yep, it's making a bond with the hydrogen to make HCl.
Okay.
Right. And then we have I minus that left as a leaving group. So it has an I minus ion.
Hmm.
Um, right, which is able to exist in this form because if we were to, let's say, compare the Cl minus charge that we have in the reactant versus the I minus charge we have in the product, this is where we determine what charge is more stable from Cario. Right. C will stand for charge. They have the same charge, negative, negative. So we don't look at that. Then we look at atom size. The
Right.
negative charge would prefer to be on the bigger atom to be more stable. Right. And from the periodic table, iodine is bigger than chlorine because it's like, I think 2 rows below chlorine. So
Hmm.
it's way bigger than chlorine. And because iodine minus is more stable, it's going to prefer to go in this reaction, in this side, in this side.
Oh, so you're comparing iodine and chlorine?
Yeah, we're comparing the I
Okay.
minus with the Cl minus. Right.
Oh, okay.
So this is an equilibrium where, oh, not an equilibrium actually. This is a reaction where it kind of is an equilibrium, but it prefers to be in the side with the I minus ion because that's the more stable side,
Hmm.
right? The I minus ion is more stable than the Cl minus, so the reaction will tend to go towards the side with the more stable molecules, right?
Okay.
More stable species. So in this reaction right here, we have OCH3 minus and NH3. That's neutral. This is going to be our base. This is going to be our acid right here, right? This base
Okay.
is going to deprotonate the acid by grabbing that hydrogen, attacking the hydrogen, and making a bond with that hydrogen. When that happens, we are deprotonating this nitrogen. So this bond right here between the hydrogen being grabbed and that nitrogen is going to break and go onto the nitrogen right there, right? To
Right.
give it an extra pair of electrons and then negative charge. So our product is going to be CH3OH and NH2 minus. But be careful here. Which negative charge is more stable? The negative charge on the oxygen or the negative charge on the nitrogen? And what factor explains that?
Mm, well, I would say if we're looking at more electronegative,
Right?
I would say the nitrogen atom. but and I would say like it's better at um like holding negative compared to um O.
Yeah. So the factor is correct. We are looking at electronegativity here, but
Right.
oxygen is more electronegative than nitrogen, right? Because on the periodic table, it's more on the right side, right? Oxygen is on the right
Oh,
side of
right,
nitrogen, and
right.
electronegativity increases from left to right and down to up, or you could think of it as this arrow right here.
Okay, I was thinking nitrogen was ahead, but my answer would have been that way if I
Yep.
remembered.
This way, right?
Yeah.
Yeah, Gen Chem, Gen Chem. Wait, does she
Yeah.
provide the periodic table? Yeah, I think she did at the first page.
Hmm.
So this reaction technically will happen, but it's going to prefer to be on the side with the O minus, right? So what they want as the product here is actually no reaction, right? But there is actually a reaction happening here, which is this reaction, but it won't like stay in this side as much, right? It's more going to be going in this direction with the more stable negative charge. So you would put no reaction as the answer, right? Because
Okay.
you don't want to form a less stable thing, right? If you see that you're
Right.
forming something less stable, put no reaction, NR, right?
So you said the more stable charge with oxygen is preferable compared to the nitrogen because oxygen is more electronegative. And so therefore, even though like they're asking us to write the products, we say it's no reaction because what they wrote out first is preferable.
Yes, yes, yes,
Okay.
that's right. But there is technically a reaction happening here, so this no reaction here is not like fully correct because there is actually a reaction happening, but um in low amounts, right? Like very like let's say if the reaction does happen, it's gonna go back to what it was before. So that's why they say no reaction.
So when you say sorry, when you say no reaction, can we say that it's a reverse reaction, like it happens and then it goes back?
You're not wrong if you say that. That's technically correct, right? That's what we put right here. Like if you do the reaction and then you draw like the reverse arrow, like bigger than the
Mm-hmm.
forward arrow, that's correct. But then they don't want that as the answer. They want NR as the answer. It's just like
Mm,
if you write this right and then you write these arrows and they take points off, then that's like a request regrade thing. Like you would request regrade and explain yourself, and then they should give
uh,
you
okay.
that. Yeah. Right. So
Okay,
this is
that
like
makes
a rubric
sense.
thing. Yeah. Like this is what is actually happening, but for the rubric, they said NR.
Right. Okay.
Right? Because they don't want to form something less stable. That's I think that's the reasoning behind that NR.
Hmm.
Right? Mhm. Okay, this C2H5 right here is going to represent that. Oh wait, no, that's C. That's three carbons. Uh, Negative charge on the carbon there, and we have this. So what do you expect is going to happen based on what we've been doing? What's going to be the base? What's going to be the acid? And what would the product look like?
Um, I think that the NaC2H5 is the base
Uh-huh.
and the H2S is the acid, and so NaC2H5 would want to deprotonate
Mm-hmm.
the H2S, and the negative would go onto this, well, we'll grab the hydrogen, and then the hydrogen will like give away that bond to sulfur,
Mm-hmm.
giving
Mm-hmm.
it the negative
Mm-hmm. Yeah. Yeah.
because the
That's
sulfur is more electronegative than the carbon,
mm-hmm. Right. So if that's the case, then it would prefer to be in this direction,
right?
right? So we can say this as the answer, with Na ion next to the sulfur, because Na is still floating around as a spectated ion. So that should be the answer. Let's check. Yep, right here.
What did you say about the Na again?
Yeah. So the Na, you know how it is positively charged, the Na ion, Na sodium
Right.
ion. You could put the answer as this, NaSH, where you know there's a positive charge on the Na and a negative charge on the sulfur, like that.
Mm,
Just like how you
okay.
know that this Na is positive, meaning that this iodine is negative, right?
Oh, okay. Um, because on the NaC2H5, that would be like a then be like a positive positive. So then technically we would want the Na to be floating around with
Mm-hmm.
the um sulfur and hydrogen.
Yes, right.
Mm,
Mm-hmm. Because that Na is a spectator ion. It's not going to do anything in the reaction. It's just spectating. It's just floating around there, and then it's attracted to a negative charge. That's why the Na here, you always see it next to a negative charge.
okay.
Yeah, it's always next to a negative charge.
Okay, that makes sense.
Yeah, right. Okay, so everything else is more Gen Chem.
Mhm.
I'm gonna move on to Kathy's questions and then go back to you with like let's do like these conceptual ones here, like the multiple
Okay.
choice ones. Yeah, let's do that. Okay, so Kathy wanted to go over 15 and 20. Number 15 and 20. 16, 15. Okay, so you said you got D, but the answer says B.
Yeah.
What is this question asking? In a carbon radical, the carbon possesses how many valence electrons? I see what it says ask. Okay. So how many valence electrons does carbon usually have based on the periodic table? And how can you determine that?
Wait, carbon
Yep, carbon.
has four.
4, right. Carbon usually has 4 valence electrons. Do you know what a radical is?
Like
Uh-huh.
when it's an unpaired
Uh-huh.
electron.
Unpaired electron or lone electron,
Yeah.
right? Not in a pair. So in a carbon radical, think of just adding one more valence electron. 4 plus 1.
Oh, that's it.
Yeah.
I thought it was counting like, oh yeah, okay. That makes sense.
Yeah. And number 20.
Yeah.
I'm trying to think of like other scenarios, because let's say we have this carbon radical, radical. And all of these carbons here. Oh, no. 2, 4, 6, 8. 1, 2, 2, 4, 6, 7. Oh, I see what you were thinking of. You were thinking of how many electrons it has to itself, right? Or like how many electrons it has. Because if we look at this example right here, this pink carbon has one, two, like we're gonna count the one it's sharing with the other atom. 1, 2, 3, 4, 5, 6, 7 electrons.
Yeah,
Right?
that's how I counted it.
Yeah, that's what you're thinking of.
Yeah. Is it only asking for the electrons to itself?
If it was asking for the electrons to itself, then it should be 4.
Wait, 5, right? Because of the
5.
radical?
Because of the what? Sorry,
The radical?
the radical. Including the radical is I'm counting 4 still. 1, 2, 3, 4, including the radical. Right. So I'm trying to figure out like where is the fifth one coming from?
Oh
Based
no,
on
he didn't, the answer key wasn't from him. It was from the I got it from, you know how the girl on the Discord, she puts
oh
up,
yeah,
yeah.
cat,
Got from
yeah.
him. So maybe it's wrong. Because he doesn't give out answer keys for his practice problems.
Did she explain why?
No, she just put it.
Let me see. Let me double check.
Oh, I'm just reading right now. She explained it. She was like, carbon has four valence electrons, but it's a radical, so it has one extra one. That's what she said.
Oh yeah. So like the explanation I gave at the beginning right here, like it has 4 electrons usually, but because it's a radical, it has one extra one, which makes it 5. But like when I'm thinking about the carbon radical in structures like this, I'm trying to figure out where the valence electrons are. Has only 3 bonds in it, and one unpaired electron resulting in a total of 7 valence electrons. 3 from the bonds and 1 is the unpaired electron. Yeah. Oh, Kathy, you are you yeah,
What?
you're correct originally.
7?
Yeah, it's 7. It's gonna be 7, right? And then I know, yeah, because okay, let me explain this again.
Okay.
Yeah. So it's gonna be 7. Yeah, ignore all this. But except the top part. The top part is like what I like drew out is correct. Right. So you know how when we make bonds, atoms want to have an octet rule, like have 8 electrons, right?
Yeah.
Carbon usually has 4 valence electrons like this. So I'm just drawing out the valence electrons of that carbon right there. Right. That I'm gonna draw out the valence electrons of another carbon atom. Like that. Right. So now when we make a bond between these 2 carbon atoms, they typically want to share them to fulfill the octet rule. Right. So from that bond, we have this right here, right? This bond is coming from these 2 electrons,
Yeah.
right? And let's say that these are hydrogens, right? But hydrogens, do you know how many valence electrons they want to be happy, to be neutral?
1.
2,
What, 2?
right? Because how many electrons can fulfill the first energy level?
2?
2, right? And the second and third energy level, 8 electrons can fulfill those, right? Where hydrogen here, to fulfill its outermost energy shell, it's only in the first one, right? It has 1 valence electron. How many more electrons does it need to fulfill its outermost shell?
1.
1, right? So it only wants 1 bond to fulfill that outermost shell. So the octet rule is like for most atoms except hydrogen, right? You could think of hydrogen as the double rule or the dubtet rule or duo rule, something like that, right? So if I draw out these bonds, now every atom is happy because every atom's outermost valence electrons are fulfilled, right? Like this hydrogen here, its first energy level, its outermost shell is fulfilled. It has 2 electrons like that, right?
Yeah.
What do we call the outermost electrons? Like
The valence
valence
electron?
electrons, right? So this hydrogen here has 2 valence electrons.
Yeah.
This carbon here, it used to have 4 valence electrons, but when we make the bonds, it has 4 bonds now. It has 8 valence electrons, right? And then because it has 8 valence electrons, its outermost shell is filled, and that fulfills the octet rule, right? Which is why this carbon is neutral. But if we draw in a carbon radical is going to have 3 bonds and 1 lone electron like that. That's a radical right there,
Yeah, that's what I was thinking.
right? And it has 1, 2, 3, 4, 5, 6, 7 electrons at its outermost shell. And that's what we call valence electrons,
Yeah.
right? So the answer is going to be 7.
Okay.
7, right? When you told me the answer was B, I was trying to think of a way to explain it, which was the first way I told you, like it has 4 valence electrons, because it's a radical, I added extra one.
Yeah,
But I
that's
was
what she did.
yeah, but I was thinking about the structures like this right here, but it didn't make sense, right?
Okay, so 7 is right.
Yeah, 7 is right because like this carbon here has 7 electrons, 2, 3, 4. It's at 7 valence electrons. Yeah, so carbon radical is gonna have 7 valence electrons.
Okay.
Yeah, that's the right answer.
Okay.
Yeah.
And then for 20,
Yeah.
because you know how you said you can just look at the table?
Yeah.
But there's none, right?
There's
That
no tertiary carbon.
yeah, that's what I was thinking. So is it
Huh?
this would the second like option be like secondary?
Yeah. You could think of bromine as wanting to go for the most substituted carbon. Substituted carbon. If tertiary is available, it prefers that tertiary carbon. If no tertiary is available, right, quaternary is more substituted than tertiary, but these reactions never work with quaternary carbons because there's no hydrogens on this quaternary carbon. Because you know how in this reaction, we have to substitute one hydrogen with the halogen.
Yeah.
These quaternary carbons here have no hydrogens to substitute with at all, right? So bromine would prefer the most substituted carbon, except the quaternary carbon, right? So if there's tertiary, then it would go for that. But if there's no tertiary, then it would go for the next substituted, which is secondary.
Oh, okay. So it would be C, right?
Yeah.
Okay.
Uh-huh. Is that right?
Well, yeah, that's what she said.
Yeah, it should be C.
Yeah.
This one here is wrong, very wrong.
Yeah, because it shouldn't be like it's breaking the octet rule, right?
Yeah, yeah. 1, 2, 3, 4, 5.
Yeah.
Uh-huh.
Oh,
Okay.
one more. Also for 21, how would you know?
Which of the following would you not expect to be formed in even small amounts? during free radical chlorination of methane? Is the answer E?
Yeah, it is. But I don't know why.
Did you go over the mechanism of free radical halogenation, like initiation, propagation, termination?
He talked about it, but yeah, I kind of get it.
Yeah, I went over this mechanism also with Elysia like some officers ago. You can watch a recording, and I went over it in detail, like what each step means, what initiation means, what propagation means, and what are the two steps of propagation, and what
Okay.
termination means. Um, but some of all of these would be formed because you would expect this to only substitute one of the hydrogens with chlorine, right? Giving you this product,
Yeah.
right? But then you could react this again with CO2 and light again, right? Which is gonna give you this, where you substitute another hydrogen with the chlorine like that, and then you go again and again and again until you like you can substitute all of the hydrogens with chlorine. Does that make sense?
Okay.
Right. So that's gonna give you A, C, and D, right? Because C is the first product you form when you substitute one hydrogen with a chlorine. Oh wait, no. That the answer's not here, right?
Mhm.
Like this answer's not here. CH3Cl is not here. Um, but this right here that I showed you is A right there,
Okay.
right? And then A, when it does the reaction again, is gonna become C. And then when C does the reaction again, it's gonna become D. So we just keep doing free radical halogenation until we get a fully chlorinated carbon like that, right? But this B right here, the one with like a CH3, that's gonna come from this termination step where we have the CH3 radical reacting with another CH3 radical, and they combine together to make the CH3 thing, right? And this is one of the termination steps, right? Which a termination step means that you are gonna start with two radicals, and then you're gonna go into zero radicals, terminating the radical chain. And I go over this in more detail in that video, like when I go over like that long mechanism, where you notice how in the reactant here, we start with two radicals, one here, another one here, and I combine them together to make a bond, which created this product here with zero radicals,
Okay, yeah. I
right?
get it.
But this is an undesired product. Like this wasn't the product we want. It's undesired,
Mhm.
right? But it can still be formed.
Okay.
Yeah. Okay. Yeah. Elysia, do you? Oh yeah, let's go over the multiple choice questions here.
Okay.
Mhm. Let's see. Okay. Which of the indicated sigma bonds is expected to be the shortest?
Um,
Whoa. What? I've only learned like single bond is the longest, double bond is like in the middle, and then triple bond is the shortest, like that.
Mm,
But then the sigma bond, they should all be the same length, I think.
that's what I I would have
What?
thought. Well, I mean, I guess they're indicating the A, B, E, C, and D, but they look the same.
Uh, huh. If I had to guess, I would pick D. Right. I'm not sure though. Let's check. Let's check. Let's check. And then if it's right, I'll explain. But we'll see. We'll see. I'll explain why I guessed that. Let's see. A. Oh, okay.
Mm.
Okay. So it turned out to be D, and I guessed D because I saw that this sigma bond was in between carbon and nitrogen, which is more electronegative than carbon is. Right. This is delayed. The Zoom. Oh, there it is. Okay. And because nitrogen is more electronegative than carbon is, nitrogen is going to pull electrons towards itself, right? So that pulling of electrons makes this bond like shorter, right? Because you could think of like shortening the bond as this nitrogen is pulling the electrons
Okay.
of carbon. Whereas the other sigma bonds, they're non-polar, right? The difference in electronegativity is negligible. So we call them non-polar bonds. But the bond here between carbon and nitrogen is polar, right? Because they create a dipole moment. Um, yeah. So sometimes they can get tricky by testing some Gen Chem like fundamentals, like the basic fundamentals. So
Huh.
be ready for like those kind of questions, like the potential of those kind of questions. And then sometimes you just have to like make an educated guess based on like what you know, and try to make connections, make dots, connect the dots, you know?
Right. Okay.
Yeah, right. Because at first when I first read this question, I was like, shouldn't they all be the same? Because like sigma one is the same. But then I saw that the difference between all of this is that all of these are non-polar bonds,
Mm,
except this one right here. And because that's polar, I just thought about like what that means, which means that nitrogen is pulling electrons to itself, and that might
mhm.
shorten the bond. But that was just a guess, and that turned out to be good.
Okay.
Uh-huh. Yeah.
That makes sense.
Uh-huh. Right. Okay. Let's move on to the next one. Which of the indicated bonds is expected to have the highest bond dissociation energy?
So when we're talking about highest bond dissociation energy, we're saying something that is basic.
Uh, when we talk about the
Or
highest
like
bond dissociation energy, we're
mm,
talking about which one is the strongest bond, like the hardest bond to break, right? Because if
okay.
you think of dissociation, you think of breaking apart, dissociate away,
Hmm.
right? So bond dissociation energy is how much energy it takes to break that bond, right?
Okay.
So it's asking for the bond that is the hardest to break. And to determine that, think of these as leaving groups, right? This I don't know why it's on the exam, but um, did you go over nucleophile, electrophile, and leaving groups yet? I don't think I don't
Um,
think so, right? I don't think you've heard those terms before. Nucleophile, electrophile, leaving group.
can I
That's like
take
the
a guess?
middle of 118A.
Or like can I guess
Yeah,
what it would
uh-huh,
be?
yeah,
I'm assuming it would be tellurium or D.
D. I'm not sure of what tellurium and selenium is, but why did you guess tellurium, or whatever that is?
I would say like because it's atomic size. Um, in like its weight, so it's like
Uh-huh.
going down its larger atom.
Right, right. Which one is the most electronegative atom? Like based on the electronegativity rule, which one is more at the upper rightmost corner of the
Oh,
table?
oxygen.
Oxygen. Yeah, so think of like whenever these bonds break, right? These bonds are
Mm-hmm.
gonna go to uh the leaving group atoms,
Mm-hmm.
right? So when they leave, they're gonna leave with these negative charges right here. Which negative charge is
Mm-hmm.
gonna be the most stable?
I would say oxygen.
Yes, oxygen. Right, right, right. So the answer should be C,
Oh, okay.
right? Because when the bond breaks, the bond has to go to some atom to give it like a pair of electrons, right? Um, and the pair of electrons is gonna be the most stable with oxygen.
Mm-hmm.
Wait, that doesn't make sense. Uh, so if this is the most stable, then this should be the easiest bond to break because it will have an easier time of breaking and going to the oxygen.
Mm-hmm.
Yeah. So, huh. The answer I think would be the one with the least electronegative atom. I don't know where selenium and Te is on the periodic table. But
Mm-hmm.
it should be the one with the least electronegative atom. I think. Wait, let's check it. Let's check it. Oh, they said C. Hmm. Highest bond dissociation energy. I think it has to C. Hmm. Yeah. I've never seen SE or TE before, so I'm not too sure of this one. Sorry, sorry.
Okay, well, like those are all in the, I think within the same row, because oxygen is top, then sulfur, then selenium, then tellurium. So I was
Uh-huh.
thinking if they're like, so they would all have the same charge. And
Uh-huh.
so I was kind of thinking if it's like something greater in weight, then it would like like it would take more for it to dissociate, or like because like to tellurium has like greater weight compared to oxygen. Oxygen has
Mm-hmm.
like the least.
Mm-hmm.
That yeah, because they're all in the same
Group.
column. Yeah.
Yeah, same column. Tellurium is Te is the biggest
Yes.
atom.
Yes.
Highest bond dissociation energy. So if it's the biggest, it should have this. I'll get back to you to this question in tomorrow's office hours. I'll have an explanation for it tomorrow. I'm gonna start it, and
Hmm.
I'll explain it to you tomorrow in office hours.
Okay.
Uh-huh.
Thank
Okay.
you.
Uh-huh. Let's see. Let's see. The hybridization of the indicated carbon atom in molecule A. Oh, so this right here is a little bit tricky, right? Because it has two double bonds. And what is another way of saying a double bond? Like instead of a sigma bond, it's
Um, sigma?
a pi bond, pi
Oh,
bond,
pi bond. Oh,
pi
okay.
bond.
Sorry.
Right. And you know how pi bond is made up of p orbitals? Like there's a p orbital here, p orbital here.
Mm-hmm.
That's that double bond right there. But there's another double bond, so that's gonna be this p orbital and that p orbital right there, right? So this carbon in the middle right here has two p orbitals, two p unhybridized orbitals. If that carbon has two unhybridized p orbitals, then it has two sp orbitals. So this carbon is sp hybridized. Wait, let's check that. Let's check that. Yeah, sp hybridized. Right.
Um, okay.
Another way you can think about it is like it has two bonding groups. That's
Oh,
probably the
okay,
easier way.
yeah. Okay, that makes sense. That's how I think of it.
Yeah.
I think when
I
like
should have
they're
just said
doing
that.
the visualizing of
Uh-huh.
like
The
I think
orbitals.
that's still a little bit tricky for me, but I get it in
Yeah.
that concept.
Right. This is the shortcut way of thinking about that, right?
Yeah.
Because if something is sp3 hybridized, it's gonna have four sp3 orbitals, zero p orbitals. If something is sp2, it's gonna have three sp2 orbitals and one p orbital. If something is
Mhm.
sp hybridized, it's gonna have two sp orbitals and two p orbitals, like that, right?
Okay.
Yeah. But uh, I could like draw it out in for you, but it's gonna take longer. And but I don't think you need to understand this concept. You just have to like know how many bonding groups it has to get the answer quickly.
Yeah.
All
Okay.
right. Yeah, but this one you have to actually visualize and see, which I don't know how to do because you don't have to like know that to answer this. Right. Now, this one, can you explain to me this one?
Yes, I think so. So, well, you would typically think that it'd be
Uh-huh.
sp3,
Uh-huh.
but there are lone pairs with the nitrogen, and it is able to do resonance. So, and like donate its electrons, or its lone pairs to the next bond, and then that bond would have five bonds, and then that double bond connected to the oxygen will want to go to the oxygen itself, and oxygen is an electronegative, um, is more like is more electronegative, I think,
Mm-hmm.
and it can handle more electrons.
Mm-hmm. Yep, that's right. And when we draw out the resonance structure, we see that this nitrogen has three bonding groups now, that double bond
Hmm.
and two single bonds. And it prefers to be the sp2 over sp3 because of resonance.
Yes.
Yeah, you got it.
Um, so I know like this one typically, like this is like something that I know now, but what is one that could also be like similar, but
Hmm.
it's like a different scenario that
Yeah.
we may get
Great.
tripped up on?
That one's gonna be something like this. What would be the hybridization of this oxygen atom here?
Um, well, I know the oxygen would have one, two, three, four. Would it have two sets of lone pairs?
Yes.
Okay, so if it has two sets of lone pairs, um, I would think that I can move its sets of electrons to the bond to the right, where it's connected with a carbonyl, and then
Hmm.
that carbonyl, like that double bond would want to go to oxygen, giving it more, its lone pairs. So then
Right.
that would mean that it is a sp2.
Yep. sp2. It is
Mm,
sp2.
okay.
If this carbonyl was not there, it would be sp3. Right. So for example, this oxygen here is sp3.
Oh, so like let's say just in general, right? If you have a carbonyl group, um, then that's like that signifies that there may be resonance
Hmm.
with
It doesn't
with
have to be a
this.
carbonyl.
Hmm.
It could also be a double bond. This
Mm.
nitrogen looks sp3, but it's actually sp2 because it can do,
It could do resonance to
yes,
the bonds to the right of it, and then that bond would go to the bond to the right of it.
to the carbon.
Yeah,
Not to the bond here. It won't make a double bond right there,
right.
right? Because this is
Okay,
an sp3 roadblock.
right. Oh, okay,
Uh-huh.
okay.
Right. So it's gonna go make a negative charge on this carbon right here.
Mm-hmm.
Right. Yeah. So that's those are the other scenarios that you might see it in. Right.
Okay, thank
Uh-huh.
you.
Yeah, no problem. Uh-huh. Okay, last question, and then we'll call it office hours. 38 and 39. Predict the major product of the following reaction. Why is it not E? Right. So chlorine prefers to be on the secondary carbon because if we draw out the table again, primary, secondary, tertiary, primary fluorine, secondary chlorine, tertiary bromine. It's not E because this is tertiary. So it's gonna be some secondary thing, which is gonna be
Oh
B.
wait, I meant yeah, I got B, but I was asking like why is it E?
Oh, the answer it said E.
Well, that's what she put, unless she's just giving wrong answers. She said because chlorine will attach to the most stable radical.
Okay, I see. I see why. Yeah. So in this case, it would be E, not B, right? This chart here is not always correct. This is like what usually is correct because you have symmetry. There's no symmetry here. If you look at the selectivity factor, right? Like this is gonna be one unique hydrogen, one unique hydrogen, one unique hydrogen, one unique hydrogen. So it's gonna be one hydrogen, one hydrogen, one hydrogen, one hydrogen times like the selectivity factor. The tertiary carbon is gonna have the highest number. So this one is gonna have the highest number right here, right? But wait, there's two hydrogens that make that. Wait. Let me make sure. Uh, hold on. Relative reactivity of chlorine. Table. Okay, I have to go to okay. Let's look at the selectivity factor and make sure that we get the right answer. CO2 light. Our unique products are gonna be this. It's not gonna react with sp2 carbons. It's only gonna react with sp3 carbons. So these are gonna be our unique products here. One, two, three more. Okay. Chlorine. No, there's two more actually. Chlorine. There it is. Okay. So we have 1, 2, 3, 4, 5 different products. Okay. So if we do the selectivity factor thing and calculate the relative abundance, we are going to have 3 hydrogens can make that one. It's primary, 3 times 1, 3. 1 hydrogen is going to make that one. 1 times 5 is 5. Okay. 2 hydrogens are going to make this one. This is secondary. Secondary, that's 4. It's 8. 2 times 4, 8. 2 times 4, 8. So the answer here is not whatever that the tertiary one is, right? It's not gonna be E.
Oh, so it's not E.
Yeah, it's not E. It's gonna be one of these ones here. This one, or this one. They're equally
Okay, so
gonna be made.
it's B.
Yep, it's B. And that's
Yeah, that's what I put. That's what I put, but she said C, E, so I was confused.
yeah, it's not E. Not E.
Okay, so it would still like if you use like the other table you made, it still works because it was
In
second.
most cases, yes. In most cases. In this case, it also works. Yeah.
Yeah. Also for 39 too, it works too, right? Because I got A, but she put B.
You got A, but she put B.
Yeah.
So if you use the table,
Oh
A.
wait, no. She put wait, hold on, sorry. She put A, but I put B.
Oh, okay, yeah. So following the table, it should be B, right? But we could compare that. 1 hydrogen makes this, but it's tertiary. So tertiary for chlorine is 5. 1 times 5 is 5. 2 hydrogens can make this product, right? 2 hydrogens can make that product, and a secondary carbon, which is going to be 4. 2 times 4 is 8. 8 is a higher number than 5, so you're gonna have more of B than A.
Okay.
Yeah.
Yeah, that's what I put too.
Right. And this is 3 times 1, that's 3. This is not possible at all, right? Because this reaction would not work with sp2 carbons. Right?
Yeah.
So it should be B, yeah.
Okay.
The chart that I give you will work with most reactions, like most products, reactants. Like all of these ones worked out with that summary chart. But to make sure for sure, yeah, you can do it mathematically like this.
Okay.
Yeah. Okay, that's good. Yeah, okay. I'll see you guys in tomorrow's office hours. Good luck, good luck.
Thank you.
Uh-huh. Yeah. Good night.
Night. Bye.
Bye. Hey Ryan. Hello, hello.
Hello. Oh
Hey.
shoot. How's your day?
It was good. It was good. How's your day?
Uh, honestly, I wasn't expecting it, but I'm also like really happy at the end of the day.
Yeah, very happy at the end of the day. What happened today?
Uh, I got invited by my friends to Taco Bell,
Mm-hmm.
like after water polo.
Yeah. That's good. Like is this a new friend from water polo or did you know him before water polo?
Um, I only knew one person, but then they just invited me, and then
Mm.
we all went to Taco Bell.
Mm-hmm.
Yeah, and I didn't have money on me, but like they said, one person was paying, so I kind of ordered like a beef quesadilla with 2 tacos. Yeah,
Oh shoot. One person ordered for the whole group?
yeah,
Oh, dang. Oh, dang. And what you get? A beef quesadilla, taco.
yeah. I first ordered like 2 bean burritos, and I realized I don't want a bean burrito, and I said scratch that. Give me this.
Yeah.
Yeah.
That's good.
Mm. Is tomorrow another long day for you?
Yeah, I have to be on campus by 6 a.m. So I have to wake up at like 4:30 ish. 4:30 ish. Yeah.
I mean, yay for weekends, you know.
Yeah, weekends.
Mm.
And I got this prize for my boba shop because
Oh, is it one of those like edible pictures that taste like nothing?
no. These this is not edible. This is a pin.
Oh.
It's a pin. It's a pin.
Mm.
Yeah, but I don't know where to put it yet. Like my backpack or I don't know where yet.
Hmm. Same schedule. I mean, okay, so I have this homework assignment I'm working on. It's different from the last one, but basically the prompt is the term overrated is often used to diminish concepts, places, roles, etc. that the speaker believes that do not deserve the prestige they commonly enjoy. For example, many writers have argued that success is overrated, or a character in a novel by Anthony Burgess famously describes Rome as a vastly overrated city, or in Queen Rania of Jordan herself has assessed that being queen is overrated. Select a concept, place, role, etc., to which you believe that the term overrated should be applied. Then write a well-developed essay that will explain your judgment. Use appropriate evidence from your reading experience or observations to support your argument.
Oh shoot. This is some controversial like discussion going on.
Yeah.
What do you have so far?
I mean, my like guess was just like overrated, like because like personal experience overrated means that like just I'm thinking about social media, just like how like
Mm,
something irrelevant like falls off immediately and like popular is like supposed to be is like used only for something that's like brand new and like not like old.
mm.
And then like my other example is probably like the 2024 Paris France Olympics.
Oh, first Fantasy Olympics?
Yeah,
Overrated. Yeah, this discussion is pretty controversial because like when you say that to your class, I think some people would like disagree, some people would agree. So it's like controversial, you know.
because not everyone thinks like or like like everyone enjoys different things, so it's gonna be
Yeah, right. So this question is like subjective, subjective to each people.
yeah. Got any ideas?
I'm trying to think right now to think of what is overrated. Probably. Hmm. Hmm.
Are you like the type of person who like enjoys like anything, even like if it like it's like really popular or not really popular, you just like enjoy whatever? And like you don't really think too hard like uh there's too
Oh,
many people there's like many people who visit Paris or like San Francisco and like
uh-huh.
it's overrated because like there's way too many people or
Oh
like
yeah.
kind of like
Right.
rave or
Yeah.
parties kind of
Like for me, I think the Super Bowl because like I have no interest in like football, so I think it's overrated for me.
was a good example.
Yeah. But like a lot of people are hyped about the Super Bowl, you know, with the halftime show, like the football players. Like I have no interest in that. So I think that's overrated for me. But
Mm,
that's my opinion. Other people might disagree.
Hey, I don't watch the football either.
Yeah, yeah, right. Uh-huh.
Hmm.
But I do enjoy watching basketball though. So I did enjoy like the Olympics
The
taking
Olympic
basketball.
with Kobe Bryant, LeBron James, everyone
Steph
else.
Curry.
Yeah.
Yeah. But the other like sports,
Uh,
I didn't like watch that much. Like the
mm,
other Olympic sports.
that's true.
Yeah.
Hmm. I mean, I feel like I could do curling. You know what curling is?
Curling? No, no.
It's like when they have the broom and they just start pushing it like
A broom and just brushing the floor?
they're brushing the floor, basically.
Oh. And is that like moving a puck or something? Moving a ball
Yeah,
or
basically.
oh yeah, I think I've seen something like that before. But I didn't know it was called curling.
Uh,
You enjoy that sport?
no, I just like think it's funny, just like
You
how it
think
became a sport. Like,
yeah.
why is it even a sport?
Yeah. Is that even in the Olympics?
It Winter Olympics probably.
Oh, it's interesting.
I mean, rock climbing and breakdancing, I feel like are new ones.
Oh yeah.
Did you like watch like the Australian breakdance competition, or did you ever like see any clips from it?
I've heard of it. But I heard that Australian people like did not even breakdance. They did something else, like some random thing, and then like people they got rid of the breakdancing sport because of them. Uh,
Yeah.
I haven't seen it.
She got a zero.
You got a zero?
Yeah.
Wait, let me switch it up. Wait, actually, I'll share my screen and we can watch it together.
I don't know if like it's available. Let's see.
Do you see my
Cause
screen
like
right
they
now?
tried like they literally just tried removing it off of Instagram. Like just like I kept trying to find like videos on Instagram and like I couldn't find any.
Oh, really? The Australian
Because no,
breakdancing
because
thing?
they like they literally just started blocking everybody or like just like removing all the content and reporting people who like just like posted that video, this reposted the same video.
They were that embarrassed. Oh my god. Wait, hold on. Let me connect this. Hello, hello.
Hello, I can hear you.
Okay, okay. Let me know if I'm cutting off. Australian breakdancing Olympics.
2024.
Okay, there. This one. Okay. Oh wait, wait. Share my sound as well. Options. Share sound. Select this option if you want others to hear sounds coming from your computer as well as see your share screen. Yes. For this. Okay. Sure. Do you see my screen?
Uh, yep, I can. Yep.
Okay, okay. Let's see what this is about.
POV, you actually got hired after lying on your resume.
Showtime, baby. Ah! What the? Oh! Boing, boing, boing. Pose. Okay, maybe this is a prank. What?
Like
Well, I
there's
guess
a
it was
whole
time to
video.
mop. Sprinkler, sprinkler.
What is going on?
I feel like it would make more sense if you watch the actual
Oh, the original one?
the actual just full thing. Yeah, full one.
What?
Hey, right, you're gonna get more viewers.
Oh my god. Oh yeah.
The Australian Olympian
This reacting to this?
for her breaking moves. Now she is defending them. Rachel Dunn, known as Reagan, is an Australian B-girl who
Wait. Hold on. Let's listen to this one.
When your bedroom has everything you need.
Wait. Sorry, what was that?
They're trying to stop you from watching this.
I know. There's so many ads. Oh, yeah.
Here we go, Reagan starting the conversation.
The whole one, yeah, this is the whole thing.
Breakdancing had everyone talking for all the wrong reasons.
Yeah.
Is that a kangaroo reference, Ronnie?
Now, breaking her silence, a week after she left fans reeling from that performance at the Paris Olympics.
I'm glad I was able to bring some joy into your lives. I didn't realize that would also open the door to so much hate, which has frankly been pretty devastating.
Australia's Rachel Gunn, better known as Ray Gunn, didn't win any medals,
So many
but
memes.
her moves launched 1,000 memes.
I'm hitting the sprinkler floor.
I got moves, so what you gonna do? I'm a worm, y'all.
Even gaining some pretty famous admirers. From Saturday Night Live's cast to Adele.
I think it's the best thing that's happened in the Olympics.
You have to wonder where Ray Gun is right now. Where's that music coming from?
And Jimmy Fallon.
Me? You want me to dance with you? All right, I can do that.
I worked my butt off preparing for the Olympics, and I gave my all, truly.
The 36-year-old, who was up against mostly younger competitors, has a PhD in sports culture and did her thesis on breaking. The Australian Olympic Committee defended her place on the team.
I'm honoured to have been a part of the Australian Olympic team.
Reagan has been shown some love online as well, including those in the breaking community writing, "We got your back." As for Reagan, she says she's off to Europe for some downtime, telling her supporters she appreciates the positivity, also supporting other Olympic breakdancers.
What the other athletes have achieved has just been phenomenal.
Thanks for watching. Stay updated about breaking news.
She got a score of 0 on the Olympics?
Yup, 0.
Oh my goodness.
And then her partner had to come in and like since like there's like 2 people from each country, like her partner had to come in and like he scored like he literally just carried her.
Oh my god. That's crazy. I didn't know that.
Because I'm in breaking club. Like yeah, just
Breakdancing club?
Yeah, basically.
Dang. The funny part was like when she was just
Watched
rolling
on the
around the
Olympics.
floor.
Yeah.
That's crazy.
It's not that like she was like a bad dancer. It's just like the skill level is just like not there
difference,
because
yeah.
she's like it was Olympic level. So like
Yeah, I know.
yeah.
What's your plan for tomorrow, Ryan? Like, what are you doing tomorrow on Thursday?
Plans for well, basically today I did not go to school because each class period was like 30 minutes. I was like,
Oh
I
yeah.
don't want to go to school. And
So your
then
parents let you
and
skip
then
school?
no, I'm gonna go to school tomorrow.
Oh no, but did your parents let you today? Did your parents school?
Yeah. Yep.
Oh, I see. Yeah. That's good.
Mm-hmm. And then tomorrow, well, actually today, yeah, I did some work. All I have is that like one thing for AP laying, and then tomorrow I'll probably wake up around like 7, and then I'll go to sleep. I mean, I'll wake up at 7, and then I go to school at like 7:20. I arrive at school, and then it's just a normal day from there. Oh yeah. So basically, today, like I went to water polo. I got invited to Taco Bell, but basically, I don't know, but I feel like I think I just got myself in like another a relationship by mistake
Oh.
because it's what's funny is that the person who paid for like my Taco Bell meal
Uh-huh.
was literally I was just like talking to her and then like I heard like and then like everyone else felt like they were third wheeling so like they literally just left me on a date with this person.
Oh shoot! So you and her were just talking alone, and they just left you guys there talking to each
No,
other.
no, they were like sitting at some other like table booth at like Taco Bell.
Right,
They're
right,
still in the
right, right.
same restaurant, but yeah.
Uh-huh. Dang. And
The
so
funny
like,
thing was is that she was just talking, like, about some other dude the whole time, like, while we were, like, in the car,
uh-huh.
and then, like, she just stopped. It's just like it's funny, it's just because, like, she kept talking about, like, telling her about someone, like, about, like, their feelings to, like, someone else, and like, "Hey, I like you," and then just, like and then she just forgot all about them.
Oh, but she was talking to you. Like she just stopped talking about them during the car
Exactly.
ride. Oh my
That was,
god.
like, in Taco Bell, but, like,
Uh-huh.
dang.
Wait, so then like, are you guys like together now, or still in
No,
the
not
talking
really.
stage?
Talking stage.
Still talking stage, yeah. Are you guys like talking to each other on Discord, text message?
It's only been, like, 30 minutes and, like, basically, she's just, like, bragging to or, like, not bragging, but, like, just telling her friends in front of me
Uh-huh.
because, like, I was, like, there was, like, 5 people, and then, like, she was just, like, telling her friends, like, about, like, how she was gonna say that she's gonna come up to this guy and, like, ask him out, and then, like and then and then she just forgot all about that person.
Oh my god. Hey, you I see you, Ryan. I see you. It's good. But how do you feel about her? Like you like her or
Uh, the thing is, it's just like she has a lot of trauma, basically.
oh, yeah.
Yeah, but like the funny thing is that like we like after because like it was 8 o'clock and like I had to go home. So basically, what happened was like we dropped her off at her house, which is super surprisingly close to mine, like 10 houses away from my house.
Mhm.
Yeah, like, I wasn't expecting that like, cause no one lives near me, not a single person. Like, I know one
Wait,
person
this
that
was
lives near
today,
me.
right?
Wait, what? Yeah, this is
This was
today.
this was today? Oh my god. Like so you
Yeah,
just like
like
got home from that whole experience?
exactly.
Oh my god.
Yeah,
Dang.
this is just today, and
Uh-huh.
then
Shoot.
yeah, but since, like, I didn't know anybody, but I'm just, like, surprised. And also, she's, like, told me about how like, her other 3 boyfriends. One just, like, broke up with her, like, 2 days before, like, her birthday.
Uh-huh.
One literally just, like oh, yeah. I guess it was, like, just, like, traumatic for her, like, but, like, she because like, all those 3 relationships were, like, pretty bad, in my
Mhm.
opinion.
Yeah. Is she the
Yeah.
same year as you?
Uh,
Junior?
Senior.
Oh, senior.
Yeah.
Senior. Okay, okay. Dang.
I don't know, it's been, like, 30 minutes of just chatting in a Taco Bell. I still don't know that much.
Still don't
So,
know much. Yeah. But do you see her in practice in water polo?
uh, it's, like, only today I saw her.
Oh my god.
Yeah, and the
Dang.
whole time she was just talking about this random dude that she's gonna say that she liked, and then she just forgot about him.
Is there practice tomorrow? Will you see her tomorrow?
Yeah, let's practice tomorrow.
Okay, okay. You should go talk to her so and see where it goes.
Yeah.
Yeah.
The funny thing is that her friends are also super surprised
Because like she just stopped talking about the guy that she was talking to with
that
her
she
friends.
liked, kind
That she
of,
liked.
but, like, never really asked out, and then she just gave up.
She just gave up and she's yeah, she forgot
Yeah,
about him.
basically.
Dang. It's curious to hear.
Yeah.
Oh my god.
I don't know. It just, like, popped out of nowhere. I just went to a Taco Bell to eat Taco Bell.
Mhm.
It's just
Dang. So
random.
you just like got into a situation accident.
Mhm.
Talking stage.
The funny thing is, like, oh yeah, I haven't told you this yet, but like, basically, in like, I have more female friends than I have male friends. But the funny thing is that like when my male, like when I have like other people like look at me, it's just like Ryan, I didn't know you were a player, and then like it basic, yeah, but like I didn't know that like I don't like see them in that way, so it's just like
Oh,
it's just
yeah.
funny to me, like
A lot of
because I just because I was just like talking to like two females and then like and just like I didn't know you like this like what they're my friends and then like it
yeah.
damn like and then everyone else is surprised. I don't know. It's just normal for me, I
Oh my
guess.
god. Normal for you. Yeah, you have like more female friends than male friends. I feel like that was me like in college and like yeah, I feel like that was me in college because most of my major were females, like biochemistry. Like
Biochemistry.
mostly people there are females. Like the females to male ratio like was so high.
Mhm.
Other majors like engineering, like there was a higher male to female ratio, but I wasn't an engineer. I was like biochemistry, healthcare
Mhm.
field. Yeah.
Mm.
All right. Dang. Hey, you're a player, right? You're a player.
Wasn't really expecting that today.
Yeah. Dang. Let me know how it goes tomorrow in office hours, but I'm gonna go walk my dog really quick, brush my teeth, and then go sleep now because I have to wake up early tomorrow.
Yeah, wake up early tomorrow. It's just
Mhm.
funny because like I never really had anything to look forward to, and like after tomorrow, because every tomorrow would just be like the same kind of like stuff I would do
Yeah.
today.
It just came out of nowhere, right? Like you weren't even looking for a relationship, and then it just came out of nowhere today. Just like
Coming out of nowhere,
today.
basically.
Yeah. So let me know. Let me know.
I was like on the 10-month grind, you know, just
Yeah.
like nothing really happened,
Uh-huh.
just because like I was just working on myself, and
So
then
yeah, it just
boom,
popped out of nowhere.
yeah.
Yeah. So let me know. Let me know how the interaction goes tomorrow and where it goes.
Yo,
Yeah.
I'm getting you more viewers.
Yeah, yeah, yeah. This is good tea. This is good storytelling here. Good tea going on. The lore is building.
It's building like 5 months already.
Yeah, that's good. That's good.
Yeah.
Yeah. Good night, Ryan. Good night. Let me
All
know.
right, good night, Brian. Yeah, see you
Yeah, good night.
tomorrow.
Yeah. See you tomorrow.
All right.